In this section, we're going to look at correlation. Correlation is a relationship that exists between the paired data values, such as between x and y values, in which something like y equals 2x. In this case, that would be the y value doubles the x value. In particular, we're going to look at linear correlations. In other words, does the data approximately fit a straight line? The linear correlation coefficient R measures the strength of the linear correlation between the paired quantitative x and y values in the sample. Rho, which looks sort of like a P, is the linear correlation coefficient of a population. So we can do a hypothesis test in which we take a sample and then use that to try and make a determination about the population of data values. You can see the equation for solving for R. Please note n is the number of pairs of the sample data. Sigma looks kind of like an E. This is sum of the indicated values. Zx and Zy refer to the z-scores of the sample values of x and y. We have one way of doing the formula here, n times the sum of the product of x and y, subtract the sum of x times the sum of y, and then all divided by the square root of n times the sum of the x squared values, subtract the sum of the x values squared, and then over here n times the sum of the y squared values, subtract the sum of the y values squared. There is a secondary way of doing this, which is the sum of the product of the Zx and Zy z-scores, all divided by n minus 1. So what we want to investigate is, with a sample of data, is there a linear correlation? A linear correlation exists between two variables when there is a correlation, and the plotted pairs, points of paired data result in a pattern that can be approximated by a straight line. And one of the things that the book really does emphasize is you can always do a calculation, but you really should look at the scatter plot, the dot plot, to see if in fact the data values form a straight line. Requirements. A linear correlation coefficient R can always be calculated, but the following should be satisfied when using paired data to make a conclusion about the linear correlation of a population. In other words, if we want to take a sample and make a conclusion about the population of data values. The sample of paired XY data is a simple random sample of quantitative data. We should really avoid voluntary responses when we can. Visual examination of the scatter plot reveals an approximately straight line pattern. Outliers should be removed if they are known to be errors. And actually you should calculate R twice, once with and without the outliers if they are not known to be errors, so that the data points that look like they're far off of what would be a straight line fit, R can be evaluated depending on whether you include them or not. Basically what you're doing there is seeing just what effect those outliers have on the value of R. Now, once we have an R value and we want to interpret it, we can do basically our hypothesis testing. The null hypothesis is that rho is 0, that there is no correlation, and the alternative hypothesis is that rho does not equal 0, and therefore there is a correlation. And so in this case, as opposed to the null hypothesis showing no effect, the null hypothesis shows no correlation. The test statistic is a t-test. T equals R over the square root of 1 minus R squared over n minus 2. It's n minus 2 because you have two variables, x and y, and each one of those has to lose 1 degree of freedom. If we want to use a p-value test, remember that we compare the p-value to the significance level alpha. We would use table 5 for the test statistic to find our p-value. If the p-value is less than or alpha, then that supports the claim of a linear correlation. If the p-value is greater than alpha, then it does not support the claim of linear correlation. So basically, if it's less than alpha, then it's more extreme in the area that it's covering, and that would support a claim of linear correlation. On the other hand, because remember, our null hypothesis is no correlation. If it's greater, then it extends further in towards the center, and that would not support a claim of linear correlation. We can also use a new table, table 11, to interpret R, to find the correlation rho significance, and basically we find the critical value. Note the critical value is always based on alpha. If the absolute value of R is greater than the critical value, there is sufficient evidence to support the claim. So if it's greater than R, then that means it's further out than, more extreme than what the critical value is. On the other hand, if it's less, then it's closer in, and therefore there would be not sufficient evidence to support the claim. So again, in both of these methods, the extreme case supports the claim of linear correlation. Something more towards the middle says there is not then sufficient evidence to support the claim of linear correlation. There are some properties for R. R is generally between -1 and 1. If it's closer to -1, then that means a negative correlation, which means basically you get a line that looks more like this. In other words, it's sloping downward as you go from left to right. When it's closer to 1, then it's very close to a line that's sloping upward from left to right. If it's close to 0, then basically you're saying that there's no real evidence for a linear correlation. Switching the values of x and y does not change R. Converting x and y values to a different scale does not change R. The value of R does not measure the strength of a nonlinear relationship, and the value of R can be greatly affected by the outliers depending on how many data values there are and the degree of those outliers. A few cautions. These methods apply to linear correlations. It may be a different kind of correlation that exists that is not linear. For example, it could be quadratic. Quadratic is like the shape of a parabola. And if you don't have the whole parabola, if you've only got the left part or the right part, it may look fairly linear when in fact it is quadratic. You can also have an exponential relationship. Exponential is like this, where it really starts to climb, but if you are down in the part in which it hasn't started to climb yet, it can look very linear. The value of R squared, the proportion of the variation in y that is explained by the linear relationship between x and y. There are some common errors despite all of this, which is even though you have a correlation, it does not mean causation. It does not mean that x causes y or y causes x. For example, there could be lurking variables in which both x and y are the result of some other factor that has not been taken into consideration. Also, if you are using average data values as opposed to the actual data values, that tends to suppress variation in the data and makes it appear more correlated than it really is. And then again, we are looking for a linear relationship and the possibility that there are relationships that are nonlinear. Now, in this particular setup, we're going to look at an example between, is there a linear correlation between the increase in a country's chocolate consumption and its increase in the number of Nobel laureates? This is a famous study that was done, I think around 2012. And so here we have 23 countries, and we are looking at their percent increase in the amount of chocolate that was consumed versus the percent increase in the number of Nobel laureates they have. There clearly are some points that are considered outliers, such as like up here or maybe down there. But, you might say, if you look that there might be a linear pattern in the data. And so that's the example that we're going to look at to determine the correlation coefficient R. Now, I've done all these things using Excel, and so it's a really handy program to go ahead and figure all these things out. So first off, here are the values of X and the values of Y. These are the same values that we were just looking at a moment ago, so you can see them. We've taken off the 1, 2, 3, 4, but basically you can see the 4.5, 5.5, 10.2, 24.3, and so forth. So there are values, our paired data, X and Y. The X part is the chocolate percent increase, chocolate consumption percent, and the Y part is the Nobel laureate increase. So here it's just X squared, so we've just taken the X value and squared it. Here's Y squared. Here is X times Y. We can sum them all, so the sum of the X's, sum of the Y's, sum of the X squared, sum of the Y squareds, and of course the mean, take your sum divided by 23. So we have the X bar, the mean of the X values, Y bar, the mean of the Y values, and then while we have it showed all of the work here, we can find the standard deviations for the X values and the standard deviation for the Y values, which means, of course, that we can take each of these X and Y values and find their z-scores. It would be, of course, X minus X bar and then divided by the standard deviation. And then here in the last column, we have the z-score for X times the z-score for Y. And then here is the sum of those. So much easier, even if it was only, say, 8 to 10 pairs of data, it's much easier to do this all in Excel. But now that I have all of these values, I can go ahead and calculate my R. Again, the R is the sum of the XY's, so that would be what we have here. Sum of the X times the sum of the Y, N, 23 in this case, and then the sum of the X squareds, the sum of the X's squared, the sum of the Y squareds, and the sum of the Y's squared. And then over here is a different way of calculating R, which is the sum of the products of the z-scores, zx and zy. And so let's go ahead and plug in all those numbers. So again, N is 23, the 207.23, that's the sum of the xy's. 133.5, that's the sum of the x's. 225, so you can see where all of those numbers are coming from. Likewise, if we take the sum of the products of the z-scores, the x times zy, and so you can see that one being calculated there. And there is our R. A note that they have come out the same regardless of which equation I'm using for finding R. So now that I have R, I can go ahead and find my test statistic. Again, the test statistic is R divided by the square root of 1 minus R squared over n minus 2. And so plugging in the numbers, I get a test statistic t-score of 6.131. Now, we want to see, in fact, if there is a linear correlation in the data. So using table 5, and again table 5 goes with t distribution. We have t 6.131 for the degrees of freedom n minus 2. So 23 minus 2 gives us the 21. The 2.831 comes from the row 21. So let us go ahead and look at table 5 real quick. So Here our t-distribution. This is the same table that we've looked at before. We're going to be looking at 21 for our degrees of freedom. Okay, so here are all the different values, and you can see area in one tail, area in two tails. We would be looking at the area in two tails here. 2.83, 2.5, 2.07, 1.7, 1.3. Notice that our 6.131 is bigger than all of them in this row. Specifically, it's bigger than the 2.8314, which is the biggest of the 5 columns shown here. And so, since it's bigger than that, then that means that the p-value has to be less than, because note, the p-value for two tails would be 0.01, and notice how the area goes up, 0.01, 0.02, 0.05, 0.1, and so forth. Well, since our t statistic is bigger than that value, then that means that the area is less than the 0.01 for two tails. And in fact, if you used Excel to calculate the p-value directly, it comes out to 0.0000044. And again, using Excel. And so definitely that is much smaller than 0.01. So since the p-value is less than 0.01, which is less than the alpha of 0.05, remember a p-value hypothesis test is always comparing the p-value to alpha. That would suggest that there is sufficient evidence to support the conclusion there is a linear correlation between chocolate consumption and a country's number of Nobel laureates. Note, if the test statistic comes between the two columns on table 5, then we would have a range of p-values as opposed to just saying, as we did in this case, because it was off the sides, that it was less than the 0.01. Now, if we wanted to use table 11 instead to make an interpretation, here's a little graph kind of to help us recognize what's going on here. Basically, there's no correlation when you're close to the middle, but if you're in the rejection zones, you're alpha on the side. If you had R of 0.413, and this is just a demonstration, and the 413 comes from our alpha of 0.05 with two tails. And again, degrees of freedom, 23 minus 2 give us 21. Alpha is 0.05 in two tails. And what we're using here is table 11. It's in the back of the book. And so you can see right there at the bottom, N is 21, area in one tail, area in two tails. Now again, this is if it's on the table exactly, we can and so there is our R. If our calculated value for R, which we have as 0.8, is beyond the 0.4 or the negative 0.4, that would be in the rejection zone. And in this case, if you're outside, then it is showing that there is a correlation. So, since the test statistic R equals 0.8 is greater than the critical value R equals 0.413, there is sufficient evidence that there is a linear correlation. And again, remember that our null hypothesis was that rho is 0, that there was no correlation. Since we are outside of that, we reject the null hypothesis and say that there is a correlation. And, honestly, if we go back to our graph for a moment, let's see, where's my graph? Oh, there we go. If we go back to the graph and just, imagine, we can kind of see there are some outliers, something way off to the side, but we can kind of contemplate that there might in fact be a linear correlation. Going up, positive correlation 0.8. It's not quite 0.1, but it definitely is approximately a linear correlation between the X and Y values, and therefore would suggest that there is a relationship between the percent increase in the consumption of chocolate and the percent increase in the number of Nobel laureates that a country has. Now, I should point out this is a famous study that was done in 2012. There is a little bit of ridiculousness about this particular comparison. One of the fallacies is the fallacy of the ecological system. In other words, these percent increases refer to the average increase of the entire country, not the average increase necessarily of individuals. And of course, it's individuals that win their Nobel Prizes, not necessarily the country as a whole. And so some caution. As we mentioned back at the beginning, you can always calculate an R, and your R may even appear to be close to 1 or close to -1, but you really should look at a scatter plot to see if in fact it makes any sense at all, whether or not the data supports falling pretty close to a linear correlation. And one thing that I would note with our plot here is if I'm looking just at the first half of the data, you might say that's a fairly tight relationship, approximately linear. But if I look at just the second half of the data, you might in fact decide that there's no correlation whatsoever. It doesn't really look like much of a straight line at all. And so it may be that the number of data points over here is influencing our overall interpretation. And so that is section 1.